Hola, hola. Hola. Vamos a dar inicio. Please have a seat. Hola, hola. Okay, so I think we can start. We can resume this session, the second one of the Mexican workshop on particles and fields. We have a set of 4 talks, short talks, and because we want to keep the time schedule. Start with this talk given by Sarai Artaya-Escatel and bottom physics at CMS. Okay, you have 10 minutes for your talk. Thank you.
Okay, thank you. Today I'm going to discuss the photon-induced processes at CMS, particularly the case of gamma-gamma to dibosons. This is gamma-gamma to WW, Z, and the light-by-light process. But firstly, how do we measure this process? Well, we have 2 paths to follow in CMS. In the case of proton-proton, for instance, in proton-proton interaction, for the case of gamma-gamma to gamma-gamma, we know that the QCD production of this process dominates a low invariant mass regime, and the QED component of this process dominates at the opposite side, higher invariant mass. And this is shown in this reference. But the same is true for the case of gamma-gamma to WW, ZZ, and Z gamma. On the other hand, in the case of ultra-peripheral collision in lead-lead, we know that, as we saw in the previous presentation, that the photon flux in this case increases to Z to the 4th. And in this case, we have access to the regime to low invariant mass for this kind of process. And why is this important? Well, these processes are sensitive to the search for new physics in the context of effective field theories. They also allow the performance to precision physics, and sometimes they are used to tune Monte Carlo predictions. Well, the first process that I would like to discuss is the gamma-gamma to WW, as well as ZZ in proton-proton by the CMS and Totem collaboration. At leading order, these are the diagrams that contribute to this process. And as we discussed before, the standard model cross-section for this production is concentrated at the low invariant mass of the boson system. So an excess over the prediction, in this case, particularly in the region of high invariant mass, could be a signal for new physics, where the measurement of the quartic coupling is sensitive to this kind of deviation from the standard model. In this analysis, the bosons were reconstructed as single fat jets, and the protons in the forward regions were they follow the reconstruction using the PPS detectors. There are 2 signal regions defined as comparing the invariant mass and the rapidity of the boson system, where the region inside of this small square correspond to the case where the two final protons are correctly associated with the jets. And in the case when one of these signal protons is missed, and one proton from the pileup production is taken instead of the signal one, the events fall in these bands. And in this plot, we see the number of events for the two channels, the gamma to WW and ZZ, sorry. And they are compared to the expected background and also for an hypothetical signal of a non-zero quadratic coupling. And we can see that there are some small excesses for the WW, maybe here, better, here for the WW channel for the different years. And we also see a small deficit for the case of the gamma to ZZ, but none of these excesses or deficits are significant. Okay. New limits in the quadratic couplings for this process are computed analyzing the energy of the system, taking into account when the unitary violation occurs in the case of WW and ZZ. And we can see that these results are more or less 15 or 20 times more stringent than the ones that we saw in the previous run. This is one parenthesis. There are many studies regarding the exclusive WW production in the search for new physics. This is a study that was performed by people from our group, and they show an anomalous coupling contribution in the high energy, sorry, in the high invariant mass regime for different anomalous couplings for this case. And the same for the gamma to ZZ. This is the result that I mentioned before. And here I will make another small parenthesis because we are also working in the gamma ZZ production to analyze these quadratic couplings, but here I'm only these are only the study of the different helicities and amplitudes for the process that were implemented in the forward physics Monte Carlo generator. So after that, we will use these, the behavior in these amplitude that were studied in this reference to try to make some constraint to these in the mass and charge for new exotic particles, but we are in that process. Okay, for the case of light by light in ultraperipheral collision in lead, the first direct evidence of this process was made by Atlas with this integrated luminosity, But there is also evidence for the light by light in ultraperipheral lead-lead collisions at CMS at 5.02 TVs with an integrated luminosity of 0.39 inverse of nanowatts. So we can see here the number of the distribution of the acoplanarity of the diphoton system, where the dots are the data, and they show also the Monte Carlo prediction for this process, as well as the main backgrounds that are the case of the production of electron pairs that are usually misidentified as photons, and also the QCD production for photon-photon. The fiducial cross-section for this process was reported as 120 nanowatts, but we see that we have some large errors if we compare with the previous talks. But they are somehow consistent with some predictions that were made for other CMS collaborators. And that's it from my side. So you have some questions?
Okay. So I am glad you are doing such an interesting work, and it was very, very nicely presented. So I didn't get if the unitarity limits was just a theory or something you are already seeing on the data.
In that case is where the prediction of the cross sections goes to a very high value that are physically.
Yeah. Okay.
Yeah.
But on measurements, you are not yet seeing it, because I mean, it's important to see where this breaks down, to see where new physics can be. Okay, thank you very much.
Thank you very much, Pablo. I don't know if somebody has some more a question. Very interesting, Sarai. That's interesting to see this result. My question is, what is the expectation for run 3 in Alice in CMS?
Yeah, that's a good question. As the previous speaker mentioned, there are a lot of efforts to keep the run, because I don't know if you know that this year we have some problems. No, well, yes, but this is one of the processes that the case of light by light that are linked to measure. We are expecting more luminosity. Also, that will help for the case of the gamma 2 set. That well, I just hope to do something with that.
I see. Okay, thank you very much. So please give thanks again, Sarai. Next question, next presentation is online presentation. I don't know if somebody can help to connect. Oh, yes, you please. Antonio, are you there?
Sí, ¿me pueden escuchar? I'm here. Can you hear me?
Yes, we can hear you very well.
Great.
You can share your screen, please. Very good.
Okay, can you see my presentation?
Yes, we can see your presentation. Coupling from per tag production proton electron collisions. Okay. Good. So you have 10 minutes, Antonio, for your talk.
Okay, 15, you mean? Okay, thank you, and good morning to all. I'm going to talk about top pair photoproduction in proton-electron collisions and its applications to the determination of top quark anomalous couplings. Okay, this talk is based on this paper that I wrote with my colleague Francisco Larios from Simvestab Mérida. Okay, I will refer to this one as reference one in what follows. Okay, very brief outline. I will talk about the effective Lagrangian at dimension 6 relevant to this process. I will talk about the process itself in semi-leptonic, top pair photoproduction in semi-leptonic mode in the standard model in proton-electron collisions. Then I will go straight to the results for dimension 6 anomalous couplings and some conclusions. There is additional material in the paper that I won't be able to cover, and this includes an extensive and hopefully exhaustive background analysis, a summary of all global SMEFT top quark analysis to date, a discussion of the limits on top dipole moments from the process B2S gamma, and a few other things. Anyways, about the dimension 6 operators, the effective Lagrangian at dimension 6 takes this familiar form. We work in the Varsov basis in unitary gauge. And there are seven basis operators that couple to the top, that couple the top to the electroweak bosons. QUB, the one I'm showing, that gives a tensor coupling of the top to the field strength tensor of the electromagnetic field. Q phi Q minus contains a vector charged coupling to the left top quark, similar to that of the standard model, plus a vector coupling of the top to the seed boson that does not play any role in photoproduction. Okay, at the LHC, W helicity fractions in top decay are not sensitive to Q phi Q minus as they are to other operators containing a charge current coupling. Okay, so Q phi Q minus is bounded only by single top production cross sections, and therefore there is less sensitivity to this operator at the LHC than there is to other charge current operators. Like, for example, QUW, which has a tensor charge coupling of the top to the W. It also has a tensor coupling to the top quark to the electromagnetic field, similar to the one in QUB, and one to the seed. However, since this operator is very well bounded by W helicity fractions in top decays, we will, in first approximation, we will ignore it. Okay, this is the same approximation that is used in an analysis by the CMS collaboration that I will quote in a moment. Okay, there are other three operators coupling the top to the electroweak vector bosons in the basis. However, this Q phi U does not contribute to photoproduction. The other two contain charge current couplings that are again well limited by W helicity fractions at the LHC, so we will ignore them. We do not expect to have sensitivity to those two operators in photoproduction in proton-electron collisions because they enter only through the decay vertex. So we will focus only on QUB and Q phi Q minus. Okay, so it will be convenient to relate the Wilson coefficients associated to these operators to more familiar parameters. The electromagnetic anomalous Lagrangian is usually written in terms of this dimension 5 operator, which contains the parameters kappa, which is the magnetic dipole moment, and kappa tilde, the electric dipole moment of the top quark. Okay, the Wilson coefficient is related to kappa and kappa tilde in this way. The charge current interaction of the top quark with the W in the standard model plus anomalous contributions can be written in terms of this dimension 4 operator with this coefficient FBL, which in the standard model is BTB. And the anomalous contributions are given by this delta FBL. Delta FBL is related to C5Q minus in this way that they are proportional to each other. Okay, I will mention that the future proton-electron colliders, we have the LHEC, which will run concurrently with the high luminosity LHC, and the FCC-HE, which will run simultaneously with the FCC-HH, and both take their proton beams from the associated proton-proton colliders. Okay, in proton-electron collider, the top pair photoproduction in semi-leptonic mode, in the standard mode, goes through these two diagrams. These diagrams are quadruply resonant, as we can see. They have two top and two W bosons in S channel. The TT bar gamma vertex is one of the production vertices in this gamma gluon collision. So that's where the sensitivity to CUV comes from. However, to preserve gauge invariance when the top and the W are off shell, additional diagrams are needed. Those diagrams can be seen as being obtained from these two diagrams, but letting the photon interact with each one of the charge decay products of the top and the T bar. There are 7 of them, so we obtain 7 additional diagrams. Okay. These diagrams are less resonant. They are triply and doubly resonant only. However, in the photoproduction regime, we cannot neglect them. Actually, there is a large destructive interference between diagrams AB and diagram CI, such that the cross-section computed with only these two diagrams and is larger by a factor 10 to 25 than the cross-section computed with all of the diagrams. Okay, of course that depends on the energy and the cuts. Since the anomalous coupling C5Q minus modifies the top decay vertex, it perturbs this cancellation, and this is where the sensitivity to C5Q minus comes in the case of this process. Okay, we define 3 photoproduction regions, depending on whether the scattered electron is detected in the forward section of the main detector, or in a forward tagger, similar to the Compton tagger, or in a very forward tagger. Okay. In region 1, we have the highest sensitivity to CUV and the lowest sensitivity to C5Q minus. In section 3, the opposite is true. And in section 2, we have moderate sensitivity to both couplings. Okay, I show here quickly the kinematic distributions for the scattered electron or the quasi-real photon. In particular, for example, we see that Q squared in photoproduction region 1 reaches down to 2 times 10 to the minus 2, and that goes down to 10 to the minus 3 GeV squared in photoproduction region 3. And well, for reference, I quote here the cross sections for the signal process and its main background, TBW photoproduction in femtobalance. Okay, we see that at the LHEC, the photoproduction cross section roughly doubles when we go from region 1 to 2, when we go from region 2 to 3. We see that the FCC-HE, the cross section is a factor of 10 larger than at the LHEC. These computations were detailed in the paper. They were carried out with MATGRAPH and PTS6 and Delphis 3.4. Okay, so now I jump to the results for C5Q minus at the LHEC and at the FCC-HE in photoproduction region 3. At 1 and 2 sigma level, assuming a measurement uncertainty of 12%, sorry. These limits are obtained only from a value for the cross-section, let's say from a measurement of the inclusive cross-sections with no other observables involved. I am expressing them in terms of delta FBL in order to compare with the projections given by the in order to compare with the results from the collaboration CMS, from this paper, which is a dedicated study of the TBW vertex. Okay, taking interval length as a measurement of sensitivity, we see that at 68% confidence level, our results are stronger than the limits obtained by CMS if we assume measurement uncertainty of 12%, but they are also stronger if we assume 15% and 18% measurement uncertainty, which are the other two values we consider in the paper. In the case of 95% confidence level limits, our limits at 12% measurement uncertainty are stronger than those obtained by CMS. At 15% uncertainty are the same, essentially, and at 18% uncertainty are a little bit looser than those obtained by CMS. Okay, for CUB, we obtain limits, the strongest limits in photoproduction region 1. These are the limits for the real part that is related to the magnetic dipole moment and the imaginary part that is related to the electric dipole moment. Okay, in the first case, there is interference with the standard model, so the limits are asymmetric with respect to 0, and they are stronger than for the imaginary part, which since the operator is CP-odd, the electric dipole is CP-odd. It has very little interference with the standard model, so here the limits are symmetric and there is a little bit less sensitivity. We compare these limits with the projections for the high luminosity LHC given by the Atlas collaboration in this reference. Based on, again, on interval length, these turn out to be somewhat stricter than the ones we obtain at the LHC and the FCC-HE. However, we must take into account that these limits were obtained from 2 process channels and taking into account as observables the inclusive cross-section and 2 differential cross-sections with 6 beams each. So we are talking here about 12, 13 different observables. So that explains the additional sensitivity they have here. We have to take this into account when we compare this projection with the results we obtain. Another interesting comparison is with very recent results from the CMS collaboration, considering only the dilepton channel. The CMS collaboration limits on CUBR are significantly looser than the ones we get. Our results are stronger in this case, and for CUB, they obtained the limits we obtain are similar to those obtained by CMS in this case. Is when CMS takes into account 2 different reaction channels, dileptonic and leptonic splagets, they obtain somewhat stronger limits for CUBR and much stronger limits for CUBI.
Antonio?
Yes.
You have 2 minutes left.
Okay.
2 minutes.
Thank you. Okay, so we have to again, we have to take into account that here there are several dozen, there are like a dozen differential cross-sections involved. So there are more than 50 observables. Okay, that's why the increased sensitivity they obtain for these limits. Okay, I will just mention that when we consider the 2-dimensional allowed regions, we find an inconsistency in the literature for the process B to S gamma that allows to the branching ratio, and the CPA symmetry allows to give limits for the magnetic dipole and electric dipole moments for the top. Like I said, we find there is an inconsistency that has not been resolved yet in between the results in these 2 references at one loop in the strong interactions. I don't have time to be more specific here. Okay, conclusions. The LHCC will provide limits on C5Q- similar to those from the high luminosity LHC. The LHCC will obtain limits on CUB stronger than those from the high luminosity LHC, and these will probably be the strongest ones until the operation of electron-positron collider begins. Okay, both sets of limits will constitute an important contribution to future global analysis. And the FCC-HE can yield improved sensitivity to both couplings relative to that of the LHC from substantially larger statistics and improved systematics. And that will be all, I guess. So thank you very much for your attention.
Thank you very much, Antonio.
Yes, yes, I hear you.
We have time for one quick question. Please, Pablo, come here.
So it's on your slide 12. You commented about some disagreement between two groups. Can you give us more details about that, please?
Yes, well, one can in principle compute the dependence of the branching ratio and the CP asymmetry of the process B to S gamma as a function of kappa and kappa tilde, the magnetic and the electric dipole moments, with next Schrödinger order cross sections in the strong interaction. Okay, and well, once we have that expression of the dependence of those branching ratio and the CP asymmetry on those parameters, we can, with the measured values, we can draw allowed regions. Here, the light blue region, the large light blue region, is the one we obtain using the result from this from the first reference. Okay, now the result from the second reference is very different, and it gives rise to the second to the smaller darker blue region that we draw here. As we can see, the results are very different, and the reason for that is that the results obtained for the branching ratio and the CP asymmetry in those two references are very different. They're inconsistent with each other. So we point out this is consistency in our paper. And so far, none of these have been disproved. Well, I guess that's for future work.
Okay, Antonio. Thank you very much again. Please, let's thank again Antonio. And we have the next contribution to this workshop. This will be Javier Murillo. Javier, are you there?
Can you hear me? Yeah, hello.
Yes, we can hear you well. Very good. And also we can see your slides. So we have Dr. Javier Murillo Quijada from Universidad de Sonora, and he will present this talk about particle production and correlations in photon-induced and diffracted events. Javier, you have 10 minutes, please, and 5 for discussion. You can start now. Thank you.
Okay, thank you. So here I will present, so most of the physics behind these processes have been discussed in the previous talks this morning. So I will just mention very specific studies that are associated with events with intact protons and intact lead ions at the LHC. And I will quickly go through forward detectors that we use to study those kind of physics, events. So if we go to slide 2, so here this was the first publication that was obtained out of this very new precision proton spectrometer that we call CT-PPS. There will be another talk on this detector by Dr. Christophe in the following days of the workshop. But here, what we aim is to detect intact protons that give rise to this, for example, central exclusive production of dileptons. So in this case, PPS is located 200 meters from the interaction point and can detect with unprecedented spatial and temporal position. The location and the timing is obtained with unprecedented precision of these protons that are not dissociated in the interaction. And you can have these other variations in where you can have a proton that fluctuates into an excited state and will not be detected by the spectrometer, but only in one site in this case and in the two sites in this case. But they will contribute to the cross section of the process. So this is already discovered. So if we go to slide 3, the top quark is a really massive particle, and we know up to now it has been observed mostly in gluon-gluon fusion events at the LHC, and then this was discovered since 1995. And up to now, and actually in the recent months, we have publication of unprecedented precision mass measurements from the top quark at the level of 0.22% and the Higgs mass of 0.12%. So this is on the most popular production channel, but the question will be, can this massive quark be produced in photoinducer events? And there are a lot of questions here that I won't have time to discuss, like this mass hierarchy problem, or the top mass being larger than the Higgs mass value. So I will go to slide 4. These are the diagrams that represent the production of the top quark in this quark-quark annihilation and gluon-gluon fusion. And here you can see one of the most popular decay channels of the top quark pair, in where you have at least 4 jets of particles, 2 corresponding to 2B jets from each of the top quarks. One of the top quarks produces another couple of B jets, light jets, giving a total of at least 4 jets of particles. You have one of the tops decaying to a lepton, with mostly we use the muon and the electron categories. In this case, it's a muon that is being detected in this side, and the presence of missing energy associated with a neutrino produced by one of the top quarks. We can use that channel to study, to mix these 2 topics and search for the top in photoinducer events, which the standard model predicts with a low rate. So you may have, so we have this approved analysis in CMS, in where you have a very small cross-section prediction, but you can enhance this by introducing anomalous couplings into the standard model that I'm not giving too many details here, but they are associated with the top quark electric and magnetic anomalous moment. And this translates into CP violation as well. This is the experimental result. That is the best upper limits we have for this exclusive central production, in where you have 2 intact protons. And this is what we call it earlier gamma-gamma fusion process. And you can see that the upper limits here are on the order of 1 picobarn. So the standard model prediction is below this, so we don't have evidence of an anomalous production. And this is the best we could do for the data set that was analyzed. So now we want to explore another process that is like, according to the standard model, is like 4 orders of magnitude more frequent than the central exclusive production, in where you have one proton that dissociates, and it's associated with this gluon that I'm pointing here. And also we have photon flux associated with the other proton that will end up intact, and then you will have this interaction that will produce a TT-bar pair. This is so there is a student at the University of Sonora that is taking this analysis and has recently joined the TTX group in CMS. So there is a lot of expectation to at least get the best upper limits for photo production in this case, with 1 intact proton. For the LHC, for protons, you can get the maximum threshold for the photon energy. You can see that you can have something that is about 0.7 TeV photon energy from one proton, compared with something like 80 to 90 GeVs from photons that come from the LED. So this is the amount of cross section that you get from this. This is compared to 1 femtobarn associated with the exclusive case that I discussed before. Also here, I won't have time to give more details, but you aside from the TT bar photo production, you have also alongside the single top production. In this case, for this these two processes are related with each other in a different way than with hadronic interactions. So in here, the production of both is very similar in terms of cross section. So each of them are quite comparable to each other in terms of production. So here, this is what we are aiming. This is the whole picture. So you have one intact proton, you have the photoproduction interaction, and you have the semi-leptonic decay with one hadronic side and one leptonic side, which this lepton could be either a muon or electron. So we did a preliminary study that was presented with the fast simulation. We were collaborating with the MACRAF authors, which this collaboration gave rise to simulation that is now being processed officially within the CMS experiment. So we are right now going towards the measurement for the single diffractive case. And here we did some toy experiment in where we were exploring possibilities of observation, taking into account the biggest or most popular background contributions. But this will of course get worse when we add some remaining contributions, but it looks quite promising. So if we go to the end of the talk, so there are other physics that you can do with intact colliding beams. In this case, you may have an intact LED nuclei that may give rise to this gamma proton interaction. This was mentioned before. This is an ultra-peripheral collision as well. And in this case, we've been studying searching for collectivity signs in small systems. We have this publication that went to PLB, which was the first exploration for photon-proton correlations, which is similar to a CEUS paper that was published on electron-proton interactions. And now we have one student that is working in another system that is the Pomeron LED system, in where we have one intact proton that is associated with this Pomeron emission. And this is under progress and under approval in the collaboration. So the question here is, can this puts under question the hydrodynamic description of the quark-gluon plasma and the reach in small systems, and there are other models under dispute, such as this model that claims for initial and final state fluctuations from the partons that participate in the interaction. Okay, so we'll have more time for this, but finally, so we can use this. So we are starting to learn more about this precision proton spectrometer. This 10 picoseconds timing precision is reducing by a very high factor the pi-log background. And at least for 1.2, we have available an amount of 115 inverse femtobarns of data available to perform these studies. Okay, and finally, for the other analysis I mentioned it, so for the case of intact lead nuclei, we don't use data spectrometer, but we can use the CDC detector that can go up to 8 in pseudo rapidity. So if we combine the action of the CDC and the hadronic forward calorimeter, we can restrict the activity in one side of the detector, which is the side where the lead nuclei is passing by, and we can get a very good signal significance that was about 95% for this publication that we did. Okay, so finally, so there are several searches and analysis that can be performed with intact protons or lead ions. We are focusing here in one analysis aiming to get the best upper limits for top photo production. We studied the correlations in small systems, specifically in photon-proton, and we are developing one analysis on Pomeron-lead interactions. For the top photo production, we obtained the simulation from MATGRAPH. We added other specifications there, like the use of the MATSPIN package, and we are running this on full simulation within CMS. So this will be shown maybe next year. And finally, in terms of the correlations studies, so the discussion is on we see that for some systems, like the photon-proton one, there is an elliptic component of the correlation distribution that is showing with a significant value, which is not zero. And this is something similar to what Atlas observes in the photon-lead system. But this is connected with not observing any rich structure in the near side or long range region. And this is what we are getting so far. There is a very recent publication by Zeus on electron-proton system that is also studying the photo production from electron-proton collisions that have comparable results than what we get with gamma proton in terms of multiplicity and significant second order coefficient. So that's all for me. Thank you.
Okay, thank you very much. Javier? Only time for a very quick question, if somebody has. Pablo, please come here.
So you are very missed here, Javier. Thank you for the talk. Let me ask you, on top photo production, when do you envisage the publication? Will you need to fight for reduced systematic uncertainties, or that is not going to be needed now? Thank you.
Yeah, so the advantage we have here is that we've been collaborating with this CMS top group, and there is an analysis which is the central exclusive background which has a very large set of systematic uncertainties indeed. But we have that previous, let's say, example to take as a starting point. But yes, of course, there are several systematic uncertainties related mostly with the jet scale. So the tops produce these jets, and we require at least four of them, and there are a lot of uncertainties related with that. But yeah.
Okay, Javier, thank you very much. So, the next talk is also online contribution, and which will be given by Michael Wilkinson. Hi, Michael. Good. Can you speak a little bit, Michael?
Yes. Hi, can you hear me?
Okay. You can open your camera if you like.
Well, I thought I had. Can you hear and see me?
Okay, no problem. That's fine. Okay, are you ready, Michael?
Yeah. No, I'm ready.
Good. So we will hear the contribution from Michael Wilkinson on behalf of the Codex collaboration, Codex B collaboration. Please, you can start now, Michael.
All right. Well, thank you very much. As has been said, my name is Michael Wilkinson. I am a postdoc at the University of Cincinnati. And I was invited here on behalf of the collaboration to tell you a bit about the Codex B experiment, what it is, and what we're trying to do. So we are aware of dark matter thanks to astronomical observations. So we know this because of things like the motions of galaxies and gravitational lensing, that there is some substance out in the universe that interacts gravitationally, but that we cannot detect electromagnetically. Now, on the other hand, we have the standard model of particle physics, which famously describes the strong, weak, and electromagnetic forces very well, but has nothing at all to say about gravity, which is the characteristic interaction of dark matter. So we know from astronomy that there is this thing in the universe that interacts gravitationally. And then in particle physics, we have nothing at all to say about it. So this is a glaring shortcoming of the standard model as it stands right now. So because the characteristic interaction is gravity, you might think that poses some challenges for detecting it, and it does, but it doesn't mean that we can't. So just because we cannot detect it electromagnetically, it doesn't mean that there isn't some other kind of feeble interplay between dark matter and the particles we know about in the standard model. So they can interact via mediators or portals, such as the scalar portal with the dark Higgs or dark scalars, the neutrino portal with heavy neutral leptons, a pseudoscalar portal with axion-like particles, or possibly a vector portal with dark photons. These are just examples, and I'll talk a little bit about some of them a little bit later. But for now, I just want to point out that these are all feeble interactions, which implies the presence of long-lived particles. So the standard model also has long-lived particles. Famously, there are muons, pions, and neutrons. So muons can decay weakly to an electron, a neutrino, and an antineutrino. Pions can decay to a muon and a neutrino. And neutrons, of course, undergo beta decay to a proton, electron, and antineutrino. And so these are all mediated by the weak force, hence the long lifetimes. So there's reason to believe that dark matter has these feeble interactions. So it's plausible that there are long-lived particles in the dark matter sector as well. So here's a plot showing the lifetimes of particles in the standard model on the vertical axis multiplied by the speed of light, so in meters, and then on the horizontal axis, their mass and GeV. And so here are the three particles I was just talking about. Pion and a muon are on the order of a meter, and then neutrons above 10 to the 10 meters. So, because this is a log scale, you can see that particles in the standard model span a very, very wide range, all the way from particles down here at the sub-nanometer level, way up to particles that we don't know if they ever decay, such as neutrons, electrons, and protons, for which we only have lower limits on their lifetimes, and in some cases above 10 to the 40 meters. So it would make sense that since standard model particles span a wide range of lifetimes, that dark matter particles would too, but conventional searches at the Large Hadron Collider focus on a small range. So conventional searches usually are limited to the sort of millimeter lifetime range, which leaves this whole region of phase space unexplored. Okay, now I have switched axes on this plot. So now the mass is the vertical axis and C tau is the horizontal axis. And so once again, you see the traditional LHC coverage, your atlases, your CMSs, and your LHCb's. covering this range with a bias away from long-lived particles. And so this phase space down here is open up to new experiments, maybe dedicated detectors. And these broadly fall into two categories, either forward or transverse detectors. So forward experiments generally focus on lighter particles produced close to the beam line. So phaser, for example, would be a small detector with about a cubic meter of volume that's been proposed to be placed along the beam collision axis several hundreds of meters downstream from either ATLAS or CMS. SHIP is another proposed forward detector. It would be located at the superproton synchrotron, the SPS, also part of the CERN complex. And then there's NA62, which is already operating at the SPS. Now, if you look over here on the plot on the right, I've switched the horizontal axis from C tau to the energy required to produce particles. And I should say, I'll talk more about transverse detectors here in a moment. But what I want to draw your attention to here is, so the lighter particles are down here, and then you have your charm quarks, beauty quarks, taus, and then you have Higgs, things like the Higgs and the top quark up here. And so the Higgs in particular, the PDG currently sets an upper limit on the branching ratio of the Higgs to something invisible, that is something that we are not able to detect at the current detectors, something like 19%. So this is a tantalizing area for new physics, right? Because of course, a lot of that is probably standard model decays that we just haven't found, but it could be new physics and beyond standard model particles. So this is an interesting area to explore. And the Higgs, of course, is only produced at the Large Hadron Collider. So if we want to explore this region of phase space, we need transverse detectors looking for long-lived particles at the LHC. So when I say transverse detectors, what I mean, so here are a number of proposed transverse detectors that would operate at the LHC. So here you have Methuselah, which is a proposed detector that would be near the CMS interaction point. So here's the beam pipe, here's the collision, and Methuselah would be way up on the surface. And it would have about 100 meter by 100 meter surface area, and then be about 25 meters or so deep. So a huge volume and a huge surface area. Again, located transverse to the beam line. Anubis would have an even larger detector volume, and it would be deployed in the shaft above the ATLAS detector, again, transverse to the beam line. ALEX is another proposal, which would reuse parts of the ALICE detector and moving the interaction point back about 10 meters in order to give space for long-lived particles to decay. And then finally, there is Codex B, which is, of course, what I'm here to talk about. So Codex B is the compact detector for exotics at LHCb. It's a proposed long-lived particle detector, and it would be a 10-meter cube in the LHCb cavern. So if you look at this schematic here on the right, you see a bird's eye view of the LHCb cavern. So this blue dot here is the interaction point where the proton collisions occur. And then you see the LHCb detector extending in this cone upward from that. Right? Again, we're looking at this from above. So Codex B would be this red square way over here, transverse to the beam line. And so it's conceived of as a zero background experiment. So it's placed here behind this existing concrete shielding wall. It's about 3 meters thick. And then we would additionally install a lead shield and a shield veto closer to the interaction point. Now, we would also integrate with the LHCb trigger. So the LHCb trigger, as of run 3, is software only. There's no hardware element to it at all, which allows a lot of flexibility in terms of the event readout. That is to say, we read out every event and do some partial reconstruction and then decide what to save. So I'll talk a bit more about all of this in a bit. So as I say, the baseline design is this 10-meter cube. So we would instrument all 6 faces and then 4 faces inside of the cube. The top and bottom faces of the cube aren't shown in this picture. And it would comprise 500 of these 2 meter by 1 meter triplet RPC panels, so resistive plate chambers, which I will explain a little more about what that means in a bit. But for now, these would follow the ATLAS Phase 2 RPC design, which is an established, inexpensive technology. This proposal also has the advantage of being placed in the LHCb cavern, which already has many of the necessary services in place. Our integration with the trigger would allow the possibility of distinguishing interesting events. Again, I'll talk more about this in a bit. Right now, we do not plan on having any kind of magnetic field or calorimeter, taking our mass measurement from geometry. So here again is this cube configuration for Codex-B, the Codex-B detector. So the 6 external faces are shown in green, and then the 4 internal faces are shown in blue. And you have the proposed location in the cavern along these axes here. So this gives you a sense of the distance, right? So this would be 26 meters in the horizontal direction from the beam line, extending 10 meters to the 36 meter mark. And right, there are 500 of these RPC triplets that comprise the detector. So when I say RPC triplet, what do I mean? Again, I'll talk a little bit more about this in a bit. But for now, you have these 3 layers to an RPC triplet, so that when a charged track comes through, you end up with this triple signal whenever there is a track. This improves the efficiency of the module overall. So what we would be looking for is an invisible particle that makes it through all of our shielding from the interaction point, and then decays in the detector volume, possibly to 2 tracks in the standard model, right? So this would be a pair of muons, for example, from the decay of this particle that made it through the shielding. And so this signal geometry is what inspired the logo for Codex-B. So you see up here this dashed line representing an invisible particle that comes down and decays into 2 tracks, which then pass through 3 layers of detector on either side, mimicking the characteristic signal that Codex-B would be searching for. Okay, so what kinds of models could we probe with this kind of signature? So there are a number of them. I'm just going to walk through this one example to illustrate. So the abelian hidden sector is a minimal model with a single new particle called a dark photon. And there's the possibility of the standard model Higgs boson decaying to 2 dark photons, here denoted A prime. And in some scenarios, this would be the dominant dark photon production mode. So if you look here on the right, you can see the sensitivity of various experiments to the branching fraction of the Higgs to 2 dark photons. So these are all upper limits that could be placed on this branching fraction. So the vertical axis is a log scale, so is the horizontal axis, which is the lifetime of the dark photon multiplied by the speed of light. And then this is for 2 scenarios, either a 500 MeV dark photon or a 10 GeV dark photon. Now, this horizontal dashed line here is the expected upper limit on the branching ratio of Higgs going to invisible at the upgraded high luminosity LHC. So I said before that right now the limit on that is about 19%. It's expected to get lower at the HL LHC, estimated to be about 6% here. So the region where this decay could take place is somewhere below that. Right? So that's the region that we really want to probe. So this is the sensitivity for several experiments. So this is, this green curve is the ATLAS detector, searching for 2 displaced vertices, right? So if the Higgs goes to 2 dark photons, which are then invisible, and then decay into 2 tracks, you end up with 2 displaced vertices potentially in the detector. And this is the region where ATLAS would be able to set an upper limit, where the high side of the band is the conservative scenario and the lower side is an optimistic scenario. Then you have here this red dashed line is the ALEX detector. So this is the phase space that it would be able to place a limit on. This is the one, sorry, this is the detector that would reuse parts of the ALICE detector. This is only possible if ALICE reached its physics goals early, giving time to install such a detector. And this gray band is Methuselah. This is the one that would be the large area surface detector above the CMS experiment. And then finally, this gold band is Codex-B. So you see here that Codex-B covers a complementary phase space to Methuselah and ALEX, although ALEX extends much lower, and can also probe some regions of phase space that Methuselah would not have access to, and definitely probe phase space that ATLAS would not in this scenario. It's a very similar story here. with the 10 GeV dark photon. This time there are two scenarios for Atlas, either the single displaced vertex or two displaced vertices in the light and the darker bands here. And so, like I said, this is just an example, but the story is very similar. So Codex-B provides a complementary phase space coverage, but it also does this at a lower cost with simplified construction and a shorter installation time. And like I said, this was just one example of the models that we would be sensitive to. Here you can see a not exhaustive list. If you want to know more about them, I encourage you to consult the reference here. Okay, so now I want to talk more about the detector. So once again, here's the LHCb cavern. Here's the proposed location for Codex-B away from transverse to the interaction point behind a couple layers of shielding. So in particular, I'd like now to explain more about what I mean by triplet RPCs, what I mean by zero background, and what integration with the LHCb trigger would do for us. So taking the last first. So as I said, in run 3, LHCb moved to a software-only trigger system. So that means that every event is read out by the hardware. And then there is a real-time reconstruction that enables flexible decisions about what events and what parts of what's at events to keep. So the Codex-B readout would integrate with LHCb and so this would allow us to use existing LHCb computing infrastructure and allow us to access LHCb data alongside Codex-B data in order to further probe the event. So this means that if we were to see a signal in Codex-B, the signature that I've been talking about with tracks originating from inside the detector volume, we would then be able to tell LHCb to save the event and also be able to analyze what LHCb noticed from the same in collision, giving us additional information about it. Yes, so the detector is comprised of resistive plate chambers, so RPCs. So you can see a schematic of how an RPC works here. So it has an insulator on either side where there are these X and Y readout strips going in opposite directions. So these on top, you see these 5, these are coming into and out of the slide. And then you see this one line down here are the strips running parallel to the slide. And so there are more coming in and out of the slide. So if you look at it from above, it's this overlapping grid pattern. So and so these strips are on either side of a gas mixture with a gap that's maintained by these spacers for uniformity. And then a voltage is placed across the gas. So when a charged particle passes through the RPC, it ionizes the gas, and you end up with these positive and negative charges, which, because you've placed them under voltage, drift in opposite directions, causing a signal to appear in both your X and your Y strips. So you have 2D information about where in the RPC the charged particle passed through. So we are not just using singlet RPCs, we're using triplets, or we would be. And so that means that if a charged particle passes through, when you stacked up these 3 singlets, you end up with these three signals from your triplet, as I showed you before. Now you have your triplet RPC. This is packaged up inside of a module, which has the support frame. So you see here the BIS-7 triplet. So this is an RPC design developed by Atlas for the upgraded LHC. It's well tested and inexpensive, and also has the desired spatial and timing resolution qualities that we would need for Codex-B. So we plan to use the same triplet design with modifications to the module as a whole. So the module contains the RPC triplet itself. It also has service connections and the support structure. So you see here that there's this aluminum frame that goes around the edges and then has these aluminum crossbars providing additional support. And you can see between the crossbars these aluminum skins that go on either side, and they provide additional support for the RPC, but they also form a Faraday cage to reduce noise in the detector. Then you have card access slots around the sides. You can see a little bit of the RPCs there through them, and you see some of the connections just dangling out here in this photo. So our RPC design would be very similar to this one. I also mentioned that Codex-B would be a zero background experiment. So what we're worried about is that primary produced neutrons and K0 longs can enter the detector and mimic signal decay. So we have, as I've said, this existing concrete wall and this additional lead shield that we want to add to help block primary produced particles. But there's a risk that the particles that we're trying to block interact with these passive shields and produce secondary decays, and thus become another source of background. Which is why we introduce a shield veto. So if you draw your attention to this cartoon here on the right, you can see again the interaction point, IP8, here where the protons collide, this blue dot. So if you follow this upper line, you see some particle produced in the interaction point, some standard model particle, I should say. And so it enters the lead shield where it interacts with the shield material, causing a decay to, in this case, a muon, which flies off somewhere. And then a second neutral particle, K0 or a neutron or what have you, that makes it through the rest of the lead and then encounters the concrete wall where it eventually is blocked and doesn't enter the detector. Okay, so that's good. That's what we want to happen. Then consider the second scenario, where a different particle is produced in the collision, and this time it makes it all the way through the lead shield, travels into the concrete wall, where it interacts and then decays, again to a muon, which flies off somewhere, as well as a neutral kaon and a neutron. And then the kaon and the neutron make it into the detector volume, where they can decay to charged tracks, mimicking our signal. So in order to avoid this, we introduced the shield veto, shown here as this gold line, which would be a single layer scintillator or something similar embedded in the lead shield. And so what this allows us to do is that if a charge track passes through here, we say, okay, well, that's dangerous, and we can reject the event. Its location is optimized using a conservative simulation. You don't want it too close to the interaction point or it blocks everything, but you also want a sufficient amount of material on the other side of it. Right, we optimized the location using simulation, and then we verified that by measuring the flux rate in the cavern. I'll talk a little bit more about this on the next slide. And then we want to conduct further background studies using the Codex Beta demonstrator detector, and I'll talk a lot more about that in a few slides. Okay, so our background simulation, we simulate a number of background particles enumerated here and here. The takeaway is that we found that they all result in less than one signal-like yield in the detector after you take account of shielding, even after collecting 300 inverse femtobarns of luminosity. So this is broken down in this table here on the right in various scenarios. I'm just going to focus on the first and last columns. You can find this table and more discussions of it at the reference here. So this first column is the yield of the various background species inside the detector volume. So here's the neutrals, here are the charged. And so these are the number of these particles that we would expect to get past the shielding and appear inside our detector volume after making certain selections. But it's okay if we have some particles in the detector volume. That's not really what we're worried about. What we're worried about is if it mimics our signal decay and there appears to be a vertex originating inside the detector volume. And so once you take into account the interaction cross sections and the decay probabilities of these particles, you end up with nil for most of these cases. And in the handful you have left, you have less than one or much less than one. And again, after 300 inverse femtobarns of data taking. I should say that the simulation does not include the machine-induced background. We're in the middle of working on that as well. Okay, so that's from simulation. We wanted to verify this with actual measurements. So we measured the hit rates in the cavern behind the concrete shield wall. So we took a scintillator shown here, and we placed it at these 4 points on the other side of the concrete shield wall in the LHCb cavern. Again, recall, here's the interaction point, here's LHCb, concrete wall. This is where we want to put Codex B. And so we placed it at these points and counted hits. And the takeaway is that the background rates were much less than we had predicted from simulation. So for example, at the second point here, we had predicted that there would be about a 5 hertz hit rate. Instead, we found that it was about 0.2. And so you can see the results here in this plot. where this red curve is the instantaneous luminosity being delivered to LHCb over time. And these blue and green curves are the hit rates measured by the scintillator at the various points enumerated here. So, right, you can see at 0.2, the green curve falls here at 0.2 hertz rather than the 5 we had anticipated. And then the second one is the same plot, just on a log scale to allow you to see the lower values. Now, these measurements are planned to be further tested by the CERN radiation group during run 3. And finally, we plan to validate our background estimates using this Codex Beta prototype detector. So this is our proposed prototype detector. It would just be a 2-meter cube in the same location that we've proposed for the big cube. Right. So the big cube is 10 meters on the side. This one's just 2 meters on the side. We would still integrate this also with the LHCb software-only trigger. And it would comprise just 14 as opposed to 500 2-meter by 1-meter triplet RPCs. But the RPCs themselves would have the same design approximately that we propose for the big detector. So here you can see a cartoon of the Codex Beta detector. You see all 6 faces would be instrumented, as well as a single interface here. And so because it is 2 meters on a side and we're using 2-meter by 1-meter RPCs, means there are 2 RPC triplets per face and 7 faces, so 14 RPCs. Finally, you can see this cartoon of the Codex Beta detector here in the room with these yellow server racks around it. You may notice that this is sort of a tight space. I'll talk a little bit more about that in a bit. So for the Codex Beta demonstrator, we would have no lead or shield veto in place, only the existing concrete shield wall, making this a good opportunity to validate our background estimates. So Codex Beta has several goals. First, validating the background estimates, as I just said. Secondly, to integrate with the LHCb readout and trigger, both to prove that it is possible and gain expertise as to how to do it. Third, to demonstrate the suitability of RPCs for this kind of detector. Fourth, to validate simulation by reconstructing standard model backgrounds. This is distinct from the first point in that we want to actually reconstruct the backgrounds, not just do hit counts. And then finally, to validate the scalable mechanical support structure for RPCs. So we have to have the support structure to hold the modules in the cubic form. We're trying to design this in a way for this 2-meter cube that we could then scale up for the big 10-meter Codex B cube. But in addition to that, there's a possibility that we might actually be able to look for new physics just with the demonstrator project. So there would be billions of B hadrons produced at LHCb while Codex Beta is in place. And so there's a possibility of B mesons decaying to a standard model signature called X, and then some dark matter candidate called Chi here. So if you look at the plot here on the right, you see on the vertical axis the upper limits on branching fractions for this decay. And on the horizontal axis, the speed of light times the lifetime of the Chi, which again is the dark matter candidate in this case. Here we assume a mass of 3 GeV for the dark matter candidate. This purple curve is what Codex B would be sensitive to. So it extends down to 10 to the minus 10 for this branching fraction for some values of the lifetime. And these blue curves here are what Codex Beta would be sensitive to, Codex Beta is not a zero background experiment for one, but even still, we would be able to probe the branching fraction at this level. Now, these gray curves are what LHCb would be able to do. Now, of course, LHCb will have more sensitivity to this than Codex Beta would. Of course, Codex Beta is just a prototype, but it's still possible for Codex Beta to be the first to place an upper limit on this using run 3 data from the LHC due to what is expected to be a simpler analysis approach due to the simplified detector. But in any case, it's really just neat to have new physics reach for a prototype at all. That's why I wanted to show you this plot. Okay, so a little bit about the electronics. As I said, LHCb has a software-only trigger. Codex Beta would integrate with the LHCb DAC, sending hits to the event builder and trigger farm on the surface. We're currently procuring strip panels for the RPC singlets. Recall that each module contains a triplet of these RPC singlets. But we've already done QA testing of a number of readout boards this past summer. Here you see a picture of the readout board, and here you see the testing. So I mentioned before that the RPC triplets are packaged into modules, which require support frames. So here you can see depicted one face of the Codex Beta cube. So you have two of these triplets side by side. They have readouts on either side. So this, the Phi readout is the long side, the Eta readout is the short side, and there's one for each module. They're called Phi and Eta basically for historical reasons. Here again, you see the cube structure. Here is a schematic of the outer frame, where you see there are these card slots along both the short and long sides, allowing for readout out electronics. And here you see a schematic of the whole module. So this green aluminum frame here with the crossbars, the red aluminum skins, and then these boxes here are the service boxes that allow for electronic and gas connections and so on. So as I said before, the design here is very similar to the BIS-7 triplet frame that I showed you before, but we would use thicker aluminum and larger cross supports. We would also have more pick points for hoisting. And we're able to do this because we have fewer space constraints to worry about in terms of fitting it into the detector. But this overall gives us a more robust and flexible design. So we've built a prototype of this frame. So here you see cuts of the original aluminum stock, which is then machined at the University of Cincinnati. And then when we assemble it, you see various parts of the assembly here. So you have these end blocks here that allow you to connect the crossbars to the outer support frames. You can see it in place in these photos. Here you can see the one of the corners of the frame and its angular reinforcements. Similar here. And then finally, you have the finished product down here. So this is an all screw assembly. There's no welding involved, and it takes about 3 hours for an inexperienced team to assemble it using just written procedures. You can see here on the right that even my youngest assistant here is able to contribute. Now, really, it has a very intuitive design. It is pretty straightforward to put together, but nonetheless has a very high precision. We're very proud of this design. Okay, so we've also done a mock RPC installation with our prototype frames. So here you can see the lower part of the frame with these aluminum shims placed across the crossbars. On top of that goes the first set of aluminum skins, recall that I mentioned before, that provide a little bit of mechanical support, but also help create this Faraday cage to improve detector noise. And then this whole thing comes together like a clamshell, right? So in here you place the RPC. For us, we just used a block of foam with the approximate dimensions. And then you just place the upper frame on top of it, again, like a clamshell, and bolt it together around the sides, along with the additional aluminum skins and shims. You can see the foam sticking out here. So, right, we've been playing around with the frame, testing it in various capabilities. So here you see some of those pick points I mentioned. So there's 4 eye bolts attached to the upper part of the frame here, connected to a hoist on the ceiling, which allows us to lift it horizontally. We also have pick points at the ends that allow us to lift it vertically. Here you can see it suspended by the hoist in the lab with Jacob standing next to it for scale. Anyway, these give us many options for manipulating the frames. This gives us flexibility for installing it in such a small space, and is also useful for mounting it to the installation carts. Both of those things I'll elaborate on more in a bit. So that's the module frames. Now, the modules themselves have to be held in place in the cubic structure, of course, which requires a support structure, which we'll have to assemble in place. So recall we have 14 about 200 kilogram modules, which are in different orientations, which lead us to roughly 3 different installation procedures. So there's the rail car orientation, where the modules are mounted vertically with rollers on the bottom to slide them into place, and then guides on the top. Then there are horizontally mounted race car, so-called modules that basically just roll into place once you get them to the correct height. And then finally, there are roll-up chambers, which would be permanently mounted to their installation carts. So we would take them into place and locate them, and they wouldn't be supported by the structure at all. They would simply sit there. Okay, right. So as I said, we're assembling this in place, but this poses some challenges. So you can see this cartoon of the server room here, where we have the walls, there are server racks, and then here is where the demonstrator cube would go. So we are constrained spatially by both the walls and the server racks. There are server racks in this location presently as well, although these would be removed ahead of our installation. But then you also see pictured here this narrow door. So it is not even 1 meter wide, and all of our components have to come through there in order to be assembled. So our proposed solutions to that involve these carts, where you have these roll-up cart, which holds them vertically, that I mentioned before, where we can use this to move most of the modules into place. And then for the last 2 modules, they would simply remain attached to the cart. We would also use this tilting cart. So for the horizontal modules are a particular challenge because they can't be oriented horizontally and also fit through the door, right? They're 1 meter wide and the door is less than 1 meter wide. So this tilting cart allows us to bring them in at an angle and then lower them down to the correct orientation in a controlled manner. And then, of course, we would assemble the support structure in place as well. While the frames are entirely screw assembly, the support structure has some welding involved. That, of course, would be done ahead of time so that in place, all we do is bolt it together. So here is the proposed production pipeline for the Codex Beta prototype. So at the University of Cincinnati, we would produce the module frames. Again, you see the prototype suspended here. We would also produce the components of the support structure, all of the welding and cutting and so on, machining. The RPC frames would then be shipped to the RPC lab at CERN, where the RPC production would take place and the modules would be assembled. And the components for the frame would be shipped to the LHCb cavern, where the modules would also be moved to for the final assembly, service installation, and of course, data taking. Right, so the support structure and installation cart design are underway for Codex Beta. The gas and electronics designs are mature. We've performed a mock installation, which you can see pictured here, where we use this wooden stand-in for modules and then manipulate it into the approximate location of the cube, taking measurements of the relevant dimensions as we go. As I showed, we have built a prototype module frame. We're in the midst of its final validation. And we're also in the middle of procuring the rest of the materials to build the prototype. Okay, so in summary, Codex B would be a new detector to search for long-lived particles in the transverse region at the Large Hadron Collider. We would have potential sensitivity to a wide range of beyond standard model scenarios, providing complementary coverage to other proposed detectors at a lower construction and maintenance cost with a relatively short construction timeline. We're aiming for a partial installation and data taking by run 4, which I think that date may have changed, nominally 2027, and with full installation by run 5 in 2032. Now, Codex Beta would be a prototype of Codex B. It would be a smaller detector, just 2 meters, just a 2 meter cube versus a 10 meter cube, but it would use the same technology and setup, integration with the LHCb trigger and so on. This would allow us to demonstrate the feasibility of the big cube as well as gain expertise and validate our background estimates. and maybe even probe new physics. As I mentioned, Codex Beta is under construction, and we're aiming for installation during the ongoing Run 3. Okay, so we are a growing collaboration at Codex B. If you find this interesting and would like to contribute, please get in touch. We would love to have you, and you can join this illustrious list of institutions that are already involved. And that's it. I'll be happy to take your questions.
Okay, Michael, thank you very much. That's very interesting and impressive progress.
Thank you.
We have some time for some questions. Pablo has one question, also myself. Okay, Pablo, please. Okay. I will ask the first question, Michael. So you are working already on the construction and proofs of this nice experimental setup using RPCs, right?
Yes.
What about the gas mixture? What about this Freon problem? Are you working on it?
Let's see. So I think you are referring to so we're looking at using this gas R134A that let's see, do I have a slide? No, I don't. So let's see, I think it's 95% tetrafluoroethane, and then some isobutane and sulfur hexafluoride as well, which, right, there's some issues with procuring that. The short answer is yes, we're aware of it and are working on it. There's a possibility of switching to other more easily procured gases at the cost of reduced performance, but right, we're exploring scenarios. I hope that answers your question.
Okay, thanks. And so you are planning to install this detector even during Run 3?
Yes.
In a couple of years or even before?
In the next couple of years, yes.
Okay. But you mentioned that the final setup, the final configuration will be for Run 5. So, okay, so it will take some time to have, so you are planning to have some interesting results or new interesting data only at that time? Or that's I don't understand that.
So, right. So with the prototype, the small cube that we are currently working to install, there is a possibility that we could produce some physics results just using prototype. But the main point of the prototype is, of course, to demonstrate the feasibility of the big detector. And so that's where we could get much more precise and potentially more interesting results. And right, so with the partial install by Run 4, this is more, this is a comment on the feasibility and of just time and effort required to get it installed. So we're hoping to get with a partially installed detector, we can still do some interesting physics with less data. I'd refer you to the references for the details on that. But then, right, with the full cube setup by Run 5 would be very helpful. I should say this timeline is very similar to that for some of these other proposed transverse detectors, which are also aiming for runs 4 or 5 for installation. It just building a detector takes a lot.
Okay. Okay, thank you. Now we have a question for Pablo, please.
Yeah, in fact, I have a question that is a follow-up of Arturo's. What you saw in invisible decays, I think it was slide 24. Can you hear me?
Yeah, I'm sorry, which slide?
I think 24.
It's on the B meson decays. No, so it wasn't 24. But for the B meson decays, yeah, this one, okay. So for instance, here, given the timelines that you have been discussing, Bell is discussing to include a detector for LLPs. And this will probably happen before you start data taking. So in this plot, in principle, you are not only competing with LHCb, but also with what the upgrade of Bell 2 will do.
Mhm. No, that's a very good point. Probably should have included Bell on this plot, but yeah, sorry, I'm not familiar enough with that proposal to make any particularly interesting comments on it. But I should reiterate that I showed this plot mostly because I think it's interesting that a prototype should have any sensitivity to this at all. But if, the prototype doesn't even compete with LHCb, while Codex B, of course, does, and it would be good to have a complementary detector to what Bell's doing. Although some of the most interesting scenarios have to do with Higgs decays, which is the motivation for putting this in at the LHC specifically.
Okay, I see. Thank you. And I also had another question on your motivation for H2AA prime at the beginning. I think, I don't remember, maybe slide 10 or something like that. Yes, this one. So for the low mass region, I'm fine for the A prime, but for the mass region close to 10 GeV, you should see something, maybe even in H2 gamma gamma deviating from standard model, and H2 gamma and missing everything also for such a high mass. And your signal on the right plot is penalized by factors of the photon A prime mixing. So I'd like to ask you about this competence, because you may see everything already on the other modes I was referring to, right?
Let's see. I'm not quite sure I understood the last part of your question, but yeah, I mean, so these are taken from this. I believe this is the expression of interest here, and the point of these plots is to show ranges of potential scenarios. Yeah, so we don't really know what it would look like, and so this the point of showing these two plots is to give a wide range of wide point of comparison between different masses for the potential masses for the dark photon. But I'm not confident that I've answered your question.
No, if you have H2 A prime, you also have H2 A prime photon and a modification of the standard model result for H2 gamma gamma. So for low mass A prime, I'm fine, but for 10 GeV, you should see something first or with H2 gamma gamma or H2 A prime gamma, or even H2 A prime gamma, which is H2 gamma and missing, and also H2 lepton anti-lepton missing. So you would see this first for sure. That's my point.
I see. Yeah, I take your point. I'm afraid I'll have to refer you to the reference here for more details on how these estimates were conducted and what was taken into account. But no, that's an interesting point. Thank you.
Okay, Michael, thank you very much again. And let's give thanks to Michael, please. Very interesting. So with this contribution, we are closing the second session, and we will resume at 2 p.m. Please, it's time for lunch now. So you can go around. There are several small restaurants also in the main square. You can find some